welcome to Unit 16, Day 4. We're going to be talking about the sum and difference identities. And at this point, we know a bunch of identities, right? We know the reciprocal identities, something like secant being 1 over cos. We know the quotient identities, tan is sine over cos. We know the Pythagorean identities, the most famous, sine squared plus cosine squared equals 1. But hopefully you have those phrases to use to remember the different Pythagorean identities, like sines cost $1. 1 cot is cozy, and then my favorite, 1 tan is secret. So if we're good with those, we're going to actually add on to our list today, and there's plenty more identities to come in this unit. And I'll give you a little bit of context as to why the sum and difference identities are going to be useful. So far, what do we know how to find the exact value for? Exact value means I don't need my calculator because we can use a special triangle to calculate the exact value. I'm actually going to draw a quick set of axes so I can say that in quadrant 1, well, first of all, we know the exact value for sine, cos, tan of 0, and all the 6 trig functions from there. But in quadrant 1, we definitely know how to find the exact value for something like an angle of 30 degrees, 45, or 60, right? Those are the special angles that we'd be working with in quadrant 1. And then we would hit once we go beyond 90, which we can evaluate all the trig functions at that angle. In quadrant 2, I want you to think about, well, what would those equivalents, if the reference angle in quadrant 2 was 30, 45, or 60, what are those actual angles? So you would get angles in order of 120, reference of 60, right? 135, and then 150. So those would be the quadrant 2 angles that we can pretty easily find an exact value for. We've got 180, and then while I'm at it, I might as well do 270, full circle, 360. If I were in quadrant 3, for example, in quadrant 3, we know that we can do the exact value of something like 210, 225, and then 240 would all be some quadrant 3 angles. I don't know if you guys can see that purple color. Those have references, right, of 30, 45, and 60. And finally, quadrant 4, the special angles would be 300, 315, and 330. So we actually know the exact value for a lot of different angles from 0 to 360. And I'll tell you, we can even accomplish more than just those by using some sum and difference identities. So if I asked you to find the exact value, again, don't touch your calculator. I want you to use some knowledge that we already have to figure out something like cosine of 15 degrees. What we're going to have to do is figure out how can I use some of the special angles that I know and combine them in a way such that we can represent that 15 degrees. So what do I mean by combine them? I mean, can we find a sum or a difference of 2 angles that would combine to give you 15? Well, if we just even analyze the quadrant 1 angles, there's a couple different options, isn't there? We can do 45 minus 30, that would be 15 degrees. We can also do 60 minus 45. That would give you the same result of 15 degrees. So what I'm going to do is I'm going to rewrite this as cosine of 60 minus 45. And what I'm going to write down is what this is definitely not the same as. It's going to be really tempting to write this as cos 60 minus cos 45. But I'll tell you, this is a function on the outside. This cosine is not a numerical value that we would distribute into the parentheses here. It's a function. And functions don't always have that capability of being able to be distributed. For example, if I said, what's the square root of 9 minus 4? That's not the same as radical 9 minus radical 4. Some of you have tried stuff like that before, but you could really quickly simplify and see that radical 5 is not equal to, well, 3 minus 2, which is 1. So the function that's a radical does not have this distributive nature either. Log functions are not distributive. If you do log of a binomial, you can't distribute the word log in there. So there has to be another way for me to evaluate cosine of 60 minus 45. So that's going to be our goal. What will I use to evaluate that if it's not equal to cos 60 minus cos 45? And that brings us to what are called the sum and difference identities. All right. So there's going to be a total of 6 of them because we're going to write the ones for sine, cos, and tan, but it's only going to look like 3. Now, Miss Crowfoot in her notes, she has them written all 6, but what I'll tell you is when I write down the sum and difference identities, I'm going to write plus or minus to account for 2 at once. So the nice thing is, like I was saying, Mrs. Crowfoot's website has it nicely separated. But I'm going to write something like this: sine of x plus or minus y. Now, to be honest, guys, there are proofs out there of these identities. You can look them up. They may involve things that we don't know yet in this course, or that we may not even get to in this course. So for that purpose, I'll avoid talking about the proof of why these work. But certainly maybe in like a pre-calc or a calculus, you might explore a little bit more as to why these identities are what they are. So for sine of x plus or minus y, the identity would be that it's sine x cosine y. And then in the middle, it's going to follow the sign of what we have in the parentheses here. So plus or minus, and then it would be cosine x sine y. So for sine, the sign stays. So you can even write that down. Sine, the sign stays the same, which is kind of cool as a way to remember. If you're adding 2 angles on the inside here, you're adding in this identity. If you're subtracting those angles, this stays subtraction. So kind of a nice way to keep track of that. Okay, for cosine. If you have cosine of x plus or minus y, what would that equal? Well, the expanded form of cosine of x plus or minus y, which we'll use to do this problem in just a few moments here, is going to be cosine x cosine y. Now, the only thing that you'll see change here is that for the sign in the middle, it's flipped. So I'm going to write that as minus over plus, meaning if you're adding the angles here, you should be finding the difference here. If you're subtracting here, then this should be a plus. And then it's going to be sine x. Oops, I'm going to go back to green here. Sine x sine y. And if you're like, hey, I really want a fun way to remember this, we got one tan is secret and one cot is cozy. Well, there's not necessarily a phrase that we use to remember this, but if we were in the halls of Fairport High School right now, you would hear these chants up and down the halls, because what do we do for something like this first identity? We read it as sine, cosine, cosine, sine. And we say it that fast. Sine, cosine, cosine, sine. And the cos one's even better. It's cosine, cosine, sine, sine. And you might even hear some clapping. Sine, cosine, cosine, sine. Cosine, cosine, sine, sine. So you'll hear me do that probably throughout the lesson. Chanting them is a good way to memorize them. And then, oh, wait, for cosine, we have a change of sign in the middle, right? If it was plus, it was minus, minus, it was plus. Cosine, C-O-S, change of sign. How cool is that? C-O-S, change of sign. Finally, we've got tan. Tan of x plus or minus y. What would that equal? All right, so for the tan equation, the top is going to be tan x and tan y, and those will be separated with a plus or minus sign. So that plus or minus will follow the same sign as what's happening in here. On the bottom, you're going to have a 1 that separates tan x times tan y. And that sign on the bottom is the opposite of whatever went in the numerator. So again, this follows the sign of that, and then the bottom's the opposite of whatever you put up here. So what's the chant for tan finally? Well, you got it. Tan, tan, 1 tan, tan. A little bit different than the sine and cosine chants, but we've got them all. Should we do them all together? I think we should. I can tell you want to clap at home, right? So we've got sine, cosine, cosine, sine. Cosine, cosine, sine, sine. Tan, tan, 1 tan, tan. And, you know, do these have to be memorized? Well, I think you probably should. All right, because I'll tell you, it's only going to help you that much more when you get to pre-calc, calc, and I know I refer to that a lot, but things all come up in those courses. So the more you commit them to memory now and you know how to use them, the better off you'll be later on. Okay, so we definitely have to know these identities. We're going to memorize them. Let's see how I'm going to use this right here, this information, specifically the cos equation, to go back and do something like cosine of 15 degrees, which was cos of 60 minus 45. Okay, so we've got to find cos 15. We know it's this. Okay. So that's going to be, if I expand that out, cosine, cosine, sine, sine, cosine 60, cos 45. And then we're going to put sine 60 and sine 45 together over here. What do I do for cos, though? Cosine, COS, has a change of sign. So this is actually going to be a plus sign in the middle. Okay. So how do I do evaluate these things? Cos 60, sine 45, you're just going to use the special triangles. And I'll see if I can draw them actually kind of real quick over here. So a 60-degree reference would have these labeled sides, right? Opposite 60's radical 3. Here's a 1, here's a 2. And for the 45-45 triangle, we've got 1, 1 radical 2 for the sides. So once you can really quickly label those, maybe you can even evaluate without drawing that picture if you've got those committed to memory. Cosine 60 is 1/2. Cosine 45, I'm just going to go right to the rationalized form of this, because this would be 1 over radical 2, which rationalizes to this. And if the expectation is simplest radical form, then you should be able to do that pretty quickly. Sine 60, opposite over hypotenuse, is radical 3 over 2. Sine 45 is actually, in rationalized form, radical 2 over 2. So then to simplify this, you're going to multiply this pair, multiply that pair, to get radical 2 over 4. Multiplying fractions, just multiply across the tops and bottoms. Over here, you would get radical 6 over 4. And then the last step is to combine it into one fraction, which I'll tell you, don't make that radical 8 up top. That's not a radical rule. Okay, but the final answer is actually radical 2 plus radical 6 over 4. That is the exact value. We've talked about exact value in a lot of contexts this year. It means not a decimal. Don't really use the calculator to get that, because the calculator is not going to tell you that cos 15 equals that. In fact, the calculator would tell you, if I take a look, that cos 15 is 0.9659. Okay, but if I fancy fraction this and do radical 2 plus radical 6 and then divide this by 4, I'm going to get that same decimal, 0.9659. So could I check in this format by typing it in the calculator? Of course, but that really won't be a major focus in this unit. I just wanted to show you what that looked like for this first example here. Okay, so now that we have that first example taken care of, let's try something like number 2. I'll make that sine 105. Okay, how would I evaluate sine of 105? Well, if I go back to my list from earlier, 105 is not one of those special angles that we can easily get the exact value for. But I bet if I look at my list of values here, I can pretty easily either find a sum or a difference that would combine to give me 105. So there's a few different things you can throw out there. I'm going to choose to add 45 and 60, because that would be a total of 105. But if anybody was thinking, what if I subtract 150 minus 45? You know what? Be a rebel. Try that and see if you get the same answer that I do. Okay. So 150 minus 45 is also a total of 105. You should get the same answer. But like I said, I'm going to try doing sine of 45 plus 60. If you did 60 plus 45, it's going to get you the same result too. Okay. All right. So this would be the identity for sine is sine, cosine, cosine, sine. So it's going to be sine 45 cos of 60 plus cos 45 sine 60. Okay, that's what the expanded version of that identity would look like. Sine, cosine, cosine, sine. Notice how the sign in the middle stayed the same. That's the trick there, to remember that that's going to stay a plus sign. So from here, what do we have to do? Well, we're just going to evaluate each of these 4 ratios and then multiply them out, add the fractions. These are all the same things I just did up here. So I'm not going to redraw these triangles again. If you have them on your paper, just refer to them when you fill in these ratios. This is going to be radical 2 over 2 simplified. And cos 60 is 1/2. Over here, cos 45 is radical 2 over 2. Sine 60 is radical 3 over 2. And if you're looking at the work from up above and you're like, this kind of sounds familiar, because we're actually going to get the same exact answer. The final answer to this one is also radical 2 plus radical 6 over 4. So apparently sine of 105 has the same exact value as cosine of 15. Don't believe me? Check it on the calc. I actually have those saved from a second ago. Yep, it's 0.9659. Probably has something to do with that whole co-function concept with sine and cosine, but I'll let you guys think about that a little bit further. Okay, so let's move on to, let's do a tan equation, because tan is kind of a fun one to chant anyway. If we do tan of 75. Okay, again, probably a lot of ways to get 75. The nice thing about these angles that we're starting with here today is that we can use all those quadrant 1 angles to really quickly get the sum or difference to be this number. 45 plus 30, that's going to stand out to you pretty quickly. I hope to get that that's 75. So tan of the sum of 2 angles. The chant for tan is tan, tan, 1 tan, tan. So we've got tan 45. Then it's going to follow the same sign on top, plus tan 30, if you use the identity correctly. On the bottom, you get 1 minus. The sign's just the opposite of what you chose on top. And the bottom is tan 45 times the tan of 30. Okay. Could we use the same pictures that we drew up at the top? Absolutely. We already have the 30, 60, 90 up here. We have the 45, 45, 90. What I might do is just redraw it from the 30-degree perspective, though, guys. So this would be the 1, the radical 3, and the 2. You don't have to do that, right? I mean, you should know where 30 is in that triangle up top. But tan 45, if you look at the triangle we drew, opposite over adjacent, isn't that just 1? Tan of 45 is 1, using the 45 reference triangle. Tan of 30 would be 1 over radical 3. And you know what? I'll rationalize that right away. Make it radical 3 over 3. Uh-oh, fractions within fractions. You know what's coming. So this is 1 minus on the bottom. Well, luckily I don't have to do any additional evaluating. It's just 1 times. And this is going to be radical 3 over 3. So if I rewrite this real quick, it's 1 plus radical 3 over 3. And then 1 minus radical 3 over 3, right? Because 1 times that would just be radical 3 over 3. We have a complex fraction whose LCD is 3. So multiply the top by 3, multiply the bottom by 3. The hardest part about a tan question is probably the algebra, to be honest. Distribute the 3 across the top, you get 3 plus radical 3. Distribute the 3 across the bottom, you get 3 minus radical 3. And guess what? We are not even close to being done. This is not in simplest radical form yet. I'm just going to rewrite my answer over here for a second. So hopefully we're okay with that step where we multiplied through by the LCD. But now we have to rationalize the denominator, a skill from quite a while back. You're going to multiply the top and bottom by the conjugate of what's down here. Oh, man. All right, so if I multiply across the top, you can do some of this maybe in your head. 3 times 3 is 9. You're going to get a 3 radical 3 and another 3 radical 3. So that's a total of 6 radical 3 from the FOIL. Radical 3 times radical 3 is a plus 3. When you multiply these conjugates on the bottom, you just have to do the first and the last. 3 times 3 is 9 minus, that's going to be a 3. So continuing to simplify here, 9 plus 3 on top is 12, plus 6 radical 3, all divided by 6. And since 6 so nicely divides into both of those, you can divide this out to get 2 plus 1 radical 3, or just 2 plus radical 3. That is the exact value for tan 75. This is the last one I'm going to check on the calculator for you. Here's tan 75, 3.732. And lo and behold, 2 plus the square root of 3 is, oh, no, hold on. I somehow did square root of theta. Don't know how I did that. All right, let's try radical 3. Yeah, there we go, 3.732. So same exact decimals there. If you're getting stuck and you're really not sure if it matches, go ahead and check it out on the calc. So yeah, some of the tan work, guys, I would say that the algebra is going to be a little bit tricky at times, but hopefully that example helps you to get through some of the practice there. All right, what else can we do other than maybe just some evaluating? There's going to be some examples where maybe you'll see it all written out already for you. So here's what I mean by that. If I gave you cos 96, cos 6, plus sine 96, sine of 6. If you're looking at this, you might get worried at first and say, hey, we don't even know the exact value for cos 96 and cosine of 6 degrees. Those don't sound like special angles, and have no fear. This is going to be one where it's already been expanded for you. So I actually want to bring this back together, almost condense it. It kind of has almost like a log property-ish feel, if you think of it that way. That if you see cosine, cosine, sine, sine, you better be thinking it's a cosine formula. It's a cosine formula. And what am I doing with these two angles in question? Well, if it's a plus sign in the formula, I know that in here it's the difference of two angles. What two angles is it the difference of? 96 and 6. So if I kind of squeeze that back into a single difference of two angles for the function cos, well, now I can see that 96 minus 6 is 90. And what is the cos of 90 degrees? Well, here's a quick graph of cosine. 90 degrees would be this location here. That whole thing is a big old 0. Cos 96, cos 6, plus sine 96, sine 6 would actually simplify to 0. So if you see something expanded out, think of which formula it is. In this case, it was a cosine formula. And for the sum for cos, it would switch over to the difference. Okay. Just a couple more I want to do with you, maybe just two more quick ones, guys. There's one in the notes that says to prove that this is true. Remember, for an identity proof, you're going to work down, just one side or sometimes both sides, but you don't cross the equal sign like you do for an equation. Okay. Prove that cos of 180 minus theta equals negative cos theta. Here we go. Draw the wall. Definitely going to be working down the left side here. We know that we have an identity for cosine of the difference of two angles. Notice how one is an angle that we're given the measure for, and the other is just kind of a general theta there. So when I expand this out, it's going to be cosine, cosine, sine, sine. That's the pattern for a cos formula. Cos 180, cos theta. The difference of those angles would make it a plus sine 180, sine theta. Okay. Once you have that written out, the only two things you can simplify are the ones where you actually have a specific angle measure. We can replace cos 180. We can replace sine 180 with the values from their graphs. So 180 would correspond with this point on the graph for cos and this point on the graph of sine. So what winds up happening is if I replace cos 180, what would I replace it with? Its value is -1 times cos theta. That's pretty good news. And then look what happens over here. Sine 180 is 0 times the sine theta. Well, -1 times cos is negative cos theta. 0 times sine theta. Bye-bye. All right. Put a whole bunch of check, heart, smiley faces on that side. That is the, that's proven the identity, that does equal negative cos theta. The last thing I just want to reference with you quick is there's an example in the notes about sine of a negative angle, -75 degrees. So to come up with the exact value for this, there's a couple different ways you can make -75. You can probably think about subtracting two angles where the bigger angle is second, because that would make the result negative. But we did 75 earlier where we combined 30 and 45, and that was no big deal. So instead of doing 30 and 45, why don't I just do -30 plus -45? Okay. So if I do that, if I think of the x and the y, the angle x is the -30, and the angle y is -45. So when I expand this sine formula out, sine, cosine, cosine, sine, it's going to be sine of -30, cos of -45. Now, I was adding those angles together, the -30 and -45. For sine, the sine stays the same, plus cosine of -30, sine of -45. Okay. Here's the only thing you really have to be cautious about here. -30 and -45, we know what to do with those reference angles. But what quadrant would we be working in? Well, -30 degrees It's an angle that's in quadrant 4, right? It's 30 degrees rotated clockwise. Same thing for negative 45. It's a quadrant 4 angle. So this would be negative 1 on the opposite side, radical 3 and 2. Here it would be negative 1, 1, and radical 2. So you're going to see some negatives thrown in the mix since we're not in quadrant 1 anymore. Okay. If you evaluate these, I might as well just finish it quick. Sine of negative 30 is negative 1/2. Makes sense. All-star trig class would tell me that in quadrant 4, sine is negative. Cos will be positive, right? All right, cos negative 45, come to this triangle, adjacent over hypotenuse, rationalize would be radical 2 over 2. All right, plus cos negative 30, come to this triangle, radical 3 over 2. Sine negative 45, opposite over hypotenuse is the ratio negative radical 2 over 2 when rationalized. So this becomes negative radical 2 over 4 plus negative radical 6 over 4 for a final answer of negative radical 2 minus radical 6 over 4. You know, when you're dealing with sine and cos in these questions, you're going to see a lot of this radical 2, radical 6 business come up a lot. So don't be surprised if you see that in a lot of the practice. But I hope that this helps to make some sense of some of the filled in notes on Mrs. Crowfoot's website. You know, certainly she has some great notes up there, but I understand it would be tough to make some sense of it without having an explanation. So we'll see you guys soon, I hope, and let us know if you have any questions.